Thanks a lot for having me, and thank you everyone for being here today. I'm really excited to share with you something I'm really passionate about and I spend most of my day doing, which is studying space fossils. So it might not be very evocative from the title here, what I'm talking about, but what I really want to talk about today is comets and interstellar comets, but I'm going to come back later to what this is. Well, comets are very interesting to study for several reasons, some of them scientific, and I'll come back to that in a minute. But first and foremost, they are absolutely beautiful objects in the sky. So I don't know who here has had the chance to see a comet with their own eyes before. Anyone? Yeah, a few. Okay. Well, if you have, I hope you remember that that's a beautiful show. For those of you who haven't had the chance, hopefully that's going to come at some point. But here you've got a picture of comet, I think it's comet Macknaud, taken in 2011 from the skies of Chile. And you can see in background on top of them some of the telescopes that I'm going to tell you about a little bit later. And so comets can be these absolutely huge objects in the sky, much bigger than the moon, with an absolutely beautiful tail that can be visible with the naked eye for the very bright ones. It doesn't happen very often that we get one that is bright enough to see with the naked eye, but when they are there, they're absolutely wonderful. Okay, that's not probably the main reason to study them. Well, it's part of why I got into studying them, because I get to look at pretty images all day, which doesn't hurt. But comets is actually really interesting as fossils from our early solar system. Why is that? Well, if we look at what a comet is, that's a very zoomed in version, let's say, from the image before. It's a different comet, but it's what it looks like from very close by. This was taken by the space mission Rosetta from the European Space Agency that really sent a probe flying on the comet for a year and took absolutely amazing pictures. So comets are big blocks of rocks, rock and ice for about 1 kilometer to a few kilometers, so the size of a small town. These comets, why we call them space fossils, is because they were formed at the very early times of our solar system. At the time, just after our sun was formed, and at the time where the planets were forming. So they were formed by aggregating together little piece of rock and ice until it grew and grew to objects that are a few kilometers big. And some of them kept growing to form planets that including the one we're standing on here today. But some of them sort of didn't get agglomerated together to form planets. So comets are sort of leftover building blocks from what makes up planets. Right? And after they were formed, planets in planetary systems, they sort of tend to move around a little bit, and that can eject comets over in very remote and cold reservoirs at the very edge of our solar system. So basically, they were formed at the same time as a planet, they were ejected very far away, and they remain mostly preserved from that time, put in the fridge for a few billion years, 4.5 billion years, let's say. And then sometimes they just come back to us, and we can really study them. But that means that those comets, whenever they come back to us, really contain information about the conditions that were existing at the time planets were forming. So really, studying comets is studying the history of our own solar system to better understand how these planets form, or we got water on Earth, because we think comets might have brought some of the water on our own Earth, and really understand how we came to be there. So hopefully I've convinced you that comets are very interesting to study. And we've been studying comets at least observing comets for centuries. The biotapestry, which I think is going to be on display in the UK, actually has a comet on it. So 11th century. So we've been scientifically measuring what comets are made of, or at least what the atmosphere around comet is made of, for 1.5 centuries at least. So it's very old science in terms of astronomy. But we're still learning things about comets every day. And even more tantalizing than our own comets here from our own solar system is that we now have what we call interstellar comets that we can study. So what's an interstellar comet? It's just a comet that was formed around another star than our sun. And we know that other stars now form planetary systems. We found planets around other stars than the sun. And quite a lot, we have thousands of them right now. And we know that because they form planets, they must, in a similar way, form comets. They must form from the same building blocks, right? And in those planetary systems, you're going to have the planets probably moving around and ejecting comets. And the same way it happened in our own solar system, when it ejects comets, they can be ejected in distant reservoirs far from their star, but they can also be ejected outside of the planetary system into the interstellar space. And that's something we've thought about for years and years, and we knew should probably happen. But we didn't have really proof that that was happening until very, very recently. So these objects are ejected into interstellar space. They fly around for sometimes, millions or billions of years. And by chance, some of them might just pass through our own solar system and just whiz by for a little bit and then be gone back on their journey into interstellar space. And that's very interesting because when you think about it, then you have a little piece of rock that at the scale of space is very close to us, right? But that sort of contains a fingerprint of what was happening around another star. And when we observe these interstellar comets, we can really start to understand, well, how planets form around other stars better. We really get, a piece of it coming directly to us. You can study these planets from very distant way with the biggest telescope. We do that all the time, but it's really, really hard because it's very, very far away. So we wanted to take advantages of those objects coming very close to us. And so we waited. We knew that was possible, but we waited for quite a while. And the first interstellar object was only discovered in 2017. It was called Oumuamua. I think it's I forgot. It's a Hawaiian term. I think it's a visitor coming from outer space. I think it means something like that. So that was a big surprise. The image there on the screen is not a real image. It's an artist impression because this was the first interstellar object and very exciting. But it was not very bright. And it was visible for a very, very short amount of time because we discovered it when it was already past the closest to the sun and the closest to us and on its way away from us. So we could only observe it for a very little bit of time and we couldn't get that much information about it. But we could see that its brightness was varying quickly and that was indicated that it probably had very elongated shape, so either like a cigar or a pancake. Which is already quite interesting, which is not the shape we see the most in the solar system. So that was quite interesting that the first one we saw was a little bit strange. It was also strange in the way that it didn't have any gas. It was a bit more like an asteroid than a comet. But there are evidence that show that it probably did have gas, it just we couldn't detect it because it was too faint. Also, instruments were not sensitive enough to detect it around it. So that one came and went. And then we waited again. That's part of the game when studying comets. You'd always have to wait for the next object that comes by. You're at the mercy of them appearing and coming to visit you. The next one we discovered was in 2019. And that was, at least for me, was a bit more exciting because it was a comet. When you say it's a comet, it means it as a coma. It's this big atmosphere around it, big halo of gas around it that's produced by the gas sort of melting when it comes from close to the sun. So the gas is melted away, it lifts the dust and produces a big atmosphere, which is how we study most of the comets. And Borisov, 2I Borisov, was much brighter than the first one, so we could observe it a bit more, and we could observe it for several months until the COVID pandemic hit, and we had to stop all observations because all observatories were closed. But we still got a lot more information about that one, and it was surprisingly similar to our own solar system comets, which was interesting in a way because you can think those bodies will form around other stars in potentially very different conditions, and so you'd expect those conditions to sort of result in different composition of these objects. So that was interesting, so that the first one we could measure the composition of was so similar to our own solar system comets. So it just made us more excited to wait for the next one and see whether the next one was also going to be a bit like our own solar system comets, and it tells us a lot if they are, but whether it was going to be very, very different, and another surprise. And the third one was discovered almost exactly a year ago to the day. It was 3rd of July, 2025. And that's what I've spent most of my year on after that. Way too much of my time was spent on that. And from the get-go, it looked quite interesting. So it was discovered when it was very far from the sun. And so we could observe it for a very long time. So from July last year, all the way through April or so, we could observe it with a large number of telescopes. So we observed it for a very long time, and a lot of astronomers around the world coordinated to observe this very interesting object. So it was really exciting to share and get results sort of in real time to see what it looked like. And we observed it with some of the biggest and best telescope in the world. So you have on the left there the James Webb Space Telescope that you've probably heard of, hopefully. So a big space telescope. The one on the right here is the Very Large Telescope in Chile, which I love to use because I used to work there for 3 years operating that very same telescope. So I'm a very big fan of it. And I had to add a picture of it here. But we did use it to observe 3I Atlas. And we found a lot of interesting things about it, but I just wanted to pick one here, otherwise I'll be speaking all day. And ask me more later if you want to. So when we do observe this interstellar object, we would really like to go and drill into the ices, get a sample and analyze it in the lab. But we can't do that, it's too expensive. And it's really hard to land a space mission on a comet. And they won't let us do it for every comet, unfortunately, as much as we would like to. So the next best thing is to observe the atmosphere around it, because the atmosphere around it is just the ice that has kind of melted off. And so it lets us know a bit what is in the ice. So we use our telescopes to observe the atmosphere around the comet, right? And what we see is we can detect the molecules that are making up the atmosphere. So what is making up the ices, right? And one of the molecules that we see a lot in comets, and we saw in 3I Atlas, is the CN. So it's just a carbon and a nitrogen atom, right? So we detect it in 3I Atlas, but not only detected the CN molecule, you have several flavors of it, if you want. So if you look at the carbon atom here in green, or to the left, you see that inside of it has proton and neutrons, and you kind of have two flavors. You have the carbon, what we call the carbon-12, and the carbon-13, which is the same atom, but just with an extra neutron in it. And so these two flavors of carbon both exist in comets, right? But what's really interesting is when we take the ratio of how much there is of one versus how much there is of the other. Because the carbon-13, so the rarer carbon flavor, is less abundant in comets. And so basically the ratio between the two can tell us about the condition really, in which these objects were formed. So it's very interesting. It's a very hard measurement to do. So we need very bright objects, very bright comets, and we need very big telescopes. And so that's what we did. We managed to detect those two flavors of carbon, so CN with a normal carbon and CN with a carbon with this extra neutron, the rarer form of carbon, and we looked at how much of each one there was. And we just compared it to our own solar system comets. And what we found was really surprising, because we've done that measurements in a lot of solar system comets and always get the same answer, roughly, within the uncertainties of our measurements, but it's always really, really stable. And then when we measured it in 3I Atlas, it was much, much higher than what we see in solar system comets. So that was a bit of a surprise. I really wasn't expecting that one. And then it got us scratching our heads for quite a while, because why is it so much bigger? I expected other of these isotope ratios to change, but that one I wasn't particularly expecting it. So we had to really think about what could be happening. What does it tell us? Because if it's different, it tells us something interesting. But what is it? And to understand that, we really had to look at the bigger picture and look at the galaxy itself, our own galaxy. So our sun and our own solar system is just one of the stars in the billions and billions that make up our galaxy, the Milky Way, right? And if we look at all the stars in our galaxy and we see all the stars, so it's not stars that have sort of lived for longer, but stars that were formed before our sun, earlier in the history of the galaxy. When we look at this ratio between the two carbons, it's quite high. It's higher than for the very young stars. And when we do models of how the star produce the elements, because stars are basically big nuclear reactors that produce elements, you see that there's very little of this rarer carbon-13 at the beginning, and then it gets produced in stars. And that's why the older stars have less of it than the younger stars. And so what this measurement tells us is basically that 3I Atlas comes from a very old star. So it was formed around a very old star, much older than our sun. We think potentially about twice older than our sun, 10 to 12 billions of years ago. So what we got here, what we got to observe for most of last year, was a piece of a star that probably doesn't exist anymore, and that was formed much earlier on in the history of our galaxy than our sun. And what it tells us, well, it's exciting in itself, at least I think, getting that piece of material from such a distant away system that we could study. But it also tells us that planets were already forming around stars at that time, and we get a view of, well, yes, that planet formation happens there. And so that's very interesting in terms of understanding how can planet form all the way around the galaxy. So we're still currently analyzing all of the images that we've got of 3I Atlas, and I'm sure we'll make more very interesting discoveries in the next few months when we keep analyzing all our data. But I think a lot of eyes are already turned to the next one. This one was so excited and so different. It's like, what is the next one going to be like? Is it going to be like that one or different in yet another completely different way, which would be extremely exciting again. And what we think, well, I don't know if some of you have heard about the Vera Rubin Observatory that's just been built in Chile, and the UK is actually a very big part of the project there. And it's going to do a big survey of the sky, so looking at the whole sky every few days. And it's going to be a discovery machine for all solar system objects, but for interstellar objects as well. And that's I didn't time this, but the LSST survey actually just started yesterday. So we're hoping that with that, we're going to discover way more interstellar objects in the coming year. They expect about once a year, but who knows? It's astronomy. We never know. It could be 5 years between the now and the next one, and then you get 3 in a year. Who knows? So we're just impatiently waiting for the next one to come and visit us. Thank you very much.
If you have any questions, please just raise your hand. I'll bring you the microphone, and then you can ask it.
Hi, thank you for a really interesting talk. You mentioned, was it the Borisov?
Yeah.
Has the gas around it because it kind of goes close to the sun and everything gets vaporized, and that's why you have the gas cloud. Does that mean that when it's further from the sun or other stars, that actually you don't necessarily have a gas cloud, or it's something much smaller? So actually you would, the classic comet with the tail wouldn't actually be a comet with a tail, it would just be a bit of rock.
Yeah, exactly. Yeah, that's what happens.
Okay.
So it basically only looks like a comet when it's close to the sun, close enough. Well, let's say it can start looking like a comet about 40 times the distance from the Earth to the sun, roughly. And then it gets sort of the coma around it gets bigger and bigger. So as the comet gets closer, and more of the ice gets melted off, because some of them melt off at very low temperatures, some others at higher temperature. So more of it gets released as it gets closer to the sun, and then it goes away and it kind of freezes over again, and then does it all again and again for all comets that just come like around the sun basically continuously.
that is cool. So does that mean we can't see 40 times from the Earth, but if we could, we wouldn't necessarily be able to see the comet because we see it because of the gas. Is that right?
Well, we could see it if we had a very, very big telescope, let's say. It's just like it's small otherwise, and it gets much brighter once you get the gas. So we could still see it because basically the little piece of rock reflects the light from the sun. So that we can see. And we sort of saw its comet, I think it was Comet Halley, that we actually observed with the James Webb Space Telescope, very powerful space telescope, when it has mostly frozen over. So we've been able to see it frozen over because of how powerful the telescope is and the fact that it was a big one. So we're starting to see it, but it's really pushing basically the limit of all the instruments that we get. But if you look at the Kuiper belt, so there's a belt of objects after the orbit of Neptune, and we send missions to bodies over there, and those tend to be like massive frozen up comets, very similar. And those we have seen with space missions that we have sent there.
Thank you so much. I wondered, is there anything that you hope that interstellar comets will tell us over the next 10, 20 years about the formation of planets? Are there any mysteries that you hope that they will help solve?
Oh, that's a very, very big question. I think one of the things is, one of the things they could help answer is how, the range of conditions around which, the range of stars around which planet can form. Because, for example, you have what we call low metallicity star. So it's stars that don't have some of the more complex elements, or the largest atom in a way, because they get produced by successive generation of stars. And the question is whether there's enough material there to form planets or not. And that's one thing, if we keep getting interstellar objects from those systems, well, it's a clue that maybe they do produce planets, really. So that's one thing. One question I'm really interested in personally is how their composition really tells us about where they form. If they form very close, very far, and what happens to them in between. And that's a really hard question to answer just looking at our own solar system, because there's so many elements that play into it. So actually getting a large number of those interstellar objects will help us answer that question.
Thank you. I think you mentioned that we had actually landed a probe on a comet.
Yes.
And I wondered what we discovered from that.
Well, that it's very hard to land a probe on a comet first. So it was from the Rosetta mission, and it bounced a bit more than it landed, just because those space missions take so long. And at the time where it was designed, we thought the surface of a comet was going to be basically sandy, and the thing they're going to have to land would almost sink into a sandy-like surface. And by the time we arrived there, we had found that, well, actually, it's a very hard surface, and it bounced around. So it's really, really hard to do that. But they managed to collect a little bit of material, and it just told us a bit more about what the ices around it were made of. And so we found out through the mission, and I can't remember if it's from the lander or from the other spacecraft that was around it, that you get very incredibly complex molecules that get formed in space. So they found an amino acid in the ices of comets. So basically the building blocks of life already exist. Those very chemically complex molecules already exist in space.
Hi, so can comets crash in Earth? Could they arrive in Earth?
They could. So that's a really good question. We actually think that it might have been a comet that caused the extinction of the dinosaurs, that would have crashed on Earth and got a lot of damage and caused the dinosaurs to die. But it's quite rare, and now we don't know of any comets or asteroids that is a direct danger to the Earth. So you have a little pieces of rock that enter the atmosphere regularly. That's what's causing shooting stars. But a lot of the very big one that could create something like the extinction of the dinosaurs, we know where they are. And so we are keeping an eye on them at all time. And we're also working on what to do if we actually one day find one that's coming towards us. And if you've heard, there was this NASA mission where what they did, they took a spacecraft and they crashed it into an asteroid to see if they could nudge it away. And it worked really well. So that's a technique that you can actually use to, if you see a comet or an asteroid that's coming towards you, you can sort of crush an asteroid and it changes the course a little bit. But if you do it far enough in advance, it could just nudge it away enough that it wouldn't hit the Earth.
Thank you for the speech, by the way. I was just wondering, how rare are comets of such a big size? Like you said about how big, like that was such a huge comet that crashed into the Earth. How rare are those comets?
Oh, it's hard to say. I'll say big comets are most comets are about 1 to 2 kilometers. We've seen a few that have about 30 kilometers. We know of 3 or 4 in hundreds of years of finding comets. Well, determining their size is very hard. And having one that's big and coming towards the Earth is probably something once every a few billion years, kind of rare event. Yes, in terms of asteroids, if you get something that could destroy a city, it's more once every few 100,000 years, for example. Just to give you, it's I think about 100 meters asteroid could wipe out a city, just to give you, and that's a few, I think, hundreds of thousands of years, roughly.
So, is it called an asteroid when it enters the Earth's atmosphere?
That's a really good question. You have the comets and asteroids are basically the same thing. It's called an asteroid when it doesn't have ice, basically, when it doesn't have a tail, or when it wouldn't get a tail when close enough to the sun. When you have a little piece of rock, either pieces of asteroids or pieces of comets that enter the Earth's atmosphere, we tend to call that meteors. And then if they fall to the ground and we recover, we see some of the bits of the rocks that are left, then it's meteorites.
Thank you. This is probably our final question.
So yeah, thank you. Linking it to space debris, can that kind of affect on seeing asteroids or comets? And how do you track space debris?
Oh, that's a really, really good question. So it could impact that. So not only space debris, but also artificial satellites. So they create sort of noise in the images, right? It's tracks in the images that could prevent us from seeing the asteroid. Sorry, and then the second part of the question. How do you track them? So you have to track them. You have specialized telescopes. So it's a whole field that's called space situational awareness. But basically, a lot of people are using small telescopes that move that can move very, very fast, and to just look at anything in space and mostly space debris to see where they are. And so they're sort of big catalogs of all the space debris we know about and where they are, so that we can know whether they are going to crash mostly into each other or into a satellite that we are using. It would be very rare that one of those crashes into a comet or an asteroid. It's mostly just creating extra light in the image that we have to sort of remove to be able to see our comets and asteroids.
Thank you so much. Please join me in giving Cyrielle a round of applause.